It's a pleasure to invite Professor Eric from the Applied Physics Laboratory at the University of Washington in Seattle. He has visited us several times for the last several years. He is here for around 10 more days if anyone wants to discuss further after the seminar. Today, we are looking forward to listening to him on ocean turbulence.
Okay, good.
And elephants.
Oh, and elephants. Yes, you're going to have to wait about 3 or 4 slides to get to the elephant. Up, man. That good? Okay, good enough. Okay, so here we go. So I'm going to talk about a bunch of things: fluid dynamics, the ocean, Lagrangian stuff, and von Neumann elephants. Talk may be a bit controversial. Please ask questions. It's a work in progress, and my co-authors only get credit for the work, not for the bad hypotheses and things. Okay, so hopefully what you'll learn about are something about the role of turbulence in the upper ocean and climate, about Lagrangian measurements of turbulence. I'm hoping that will be more general than this particular application, and some ideas about how you do parameterizations of turbulence. Okay, so talking about the ocean surface boundary layer. That's the upper few hundred meters of the ocean, and it's turbulent. Typically, gosh, get rid of this. Maybe I'll go here. I want to be able to see the screen and see you guys too. Is this okay for the video? Okay, good. So these are typical profiles of temperature at that spot there in the ocean. You see that. You see near the surface, there tends to be a weakly stratified layer there. That's called the mixed layer typically, and sometimes it's shallow like there, and sometimes it's sort of deep. And the simplest characterization of what's going on is there's a layer that's got a certain depth. And exactly what that depth is difficult to define, but it's a useful concept. And that's present more or less everywhere in the ocean. For instance, this is in the wintertime in the Northern Hemisphere. This is from there. You see some places like here in the Northern Atlantic where this layer is hundreds or thousands of meters deep, goes all the way to the bottom of the ocean. And that's the way that a lot of stuff that comes out of the atmosphere goes to the deep ocean. So this is a really important place for climate. But everywhere in the Northern Hemisphere, you get sort of deep layers, blues, greens in the winter hemisphere, and much shallower values in the summer hemisphere, and it's the other way around in the other season, of course, with the deep layers being now in the Antarctic. This surface layer is a really critical part of the climate system. It obviously stores and releases heat and other things, like I showed in the last slide. And most of the biological productivity in the ocean occurs here, reminding you that about 30% of the CO2 that we've put into the atmosphere ends up in the ocean. And the way it gets to the ocean is through the upper ocean boundary layer. It has impacts on a wide range of scales. The intensity of tropical cyclones, hurricanes depends quite a lot on that layer. Monsoon oscillations, in other words, whether it's going to rain next week here, depend quite a lot on that. Marine heat waves, obviously annual cycle. And for the larger climate system, just some teasers, there are suggestions in the literature that you wouldn't even have monsoons unless the layer was a certain thinness. And if you look at the variability between the different CMAP climate models, a good fraction of that is probably due to how the models deal with this layer. So we have to model this, we have to parameterize it in ocean and climate models, and that's what this talk is about. So here's a little bit more on the physics of the upper ocean. Okay, so you've got some sort of mixed layer, you've got some sort of layer near the surface where the waves and the wind are acting directly on the ocean. Underneath it, the ocean is stratified, so the ocean's a stratified fluids problem. And there's an entrainment layer. Basically, the layer can get deeper or thicker. Turns out that a couple other things matter a lot. Lateral effects matter, but I'm going to ignore them. The surface waves matter a lot in a subtle way. The Stokes drift of the surface waves are a large driver of the physics. That's only been realized in about the last couple of decades. And the solar absorption coefficient matters a whole lot too. But in general, you've got some system. What you need to do is answer the questions, what's the physics of this? And given that, how do we model it? And that brings us to the elephants. So how do we make good models of physical systems? It's a good story here, an old hoary physics story. In 1953, Freeman Dyson and Enrico Fermi, both of who were atomic bomb scientists, had a conversation in which Freeman Dyson met with Enrico Fermi and with some theory, and Fermi said, your theory is wrong. Fermi says, there are two ways to do calculations in theoretical physics. One way is to have a clear physical picture of the process you're calculating. The other way is to have a precise and self-consistent mathematical formulation. You, Dyson, have neither. Okay, so he wasn't being nice, but he might have been right. Dyson said, well, my theory matches your data. And Fermi says, well, how many arbitrary parameters do you have? And there were 4 of them. And so then Fermi quotes von Neumann, with 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. This is a challenge to recreational mathematicians. So if you have 4 parameters, what sort of elephant can you get? Well, that's the elephant you could get. And you can make him wiggle his trunk too. And so that's von Neumann's elephant. And just as a side note, well, in some sense, AI is fitting the entire world with 1 billion parameters. We can talk about that later if you'd like. And that's probably where the hallucinations come from, is if you're outside the parameterization regime, it says all sorts of odd things. Okay, but for fluid mechanical turbulence, there's been 100 years of people trying to make self-consistent mathematical formulas. And so we can forget about that part. And therefore, what you're left with are, since turbulence models tend to have a large number of adjustable parameters, you're in a big danger of being an elephant. And so you need Fermi's clear picture. And that's what this talk is about, is trying to get a clearer physical picture of how the turbulence in the upper ocean boundary layer works. So we have an upper ocean boundary layer. There's some parameterization schemes. How good are they? A nice paper by Lee in 2019 who says, assessing parameterization scale is challenged by the lack of appropriate truth for evaluation. The truth basically consists of a lot of measurements of the depth of the layer and a few turbulence measurements in a lot of places. That's a bit of a challenge for me. My job, I've been working for decades. Me and my friends have been working a lot for decades to try to measure the boundary layer, and apparently the people in the models say none of that data has been of any use to us. That's the motivation for this talk and this line of research. What appears to be the most useful truth these days are LAS simulations, which are an interesting form of truth. And this is an evaluation of a whole pile of different models, with the metric being the change in potential energy of a layer that's deepening in time. So this is the metric. 1 is good. Numbers other than 1 aren't good. And this is relative to some LAS simulation. And there's 2 physical regimes. One is a convectively driven regime. In other words, I'm going to cool off the surface. I'm going to do convection. That's a pretty simple problem. It's really only got 1 parameter, the forcing rate, and maybe the layer depth. There's only 1 non-dimensional parameter, so it's real hard to get wrong because it's a simple problem. And therefore, the models all do pretty well, except for that guy that's clearly wrong. So that's good. Much more complicated regime is when the wind or the waves are forcing. There's a lot more parameters, like what direction is the wind? What direction are the waves? How big are the waves? What about the different waves? A lot of different parameters. And so it's a much more complicated problem, and the models are all over the place, plus or minus 20%. Okay. Makes you think that not all of these guys can be right. Somebody's an elephant or something like that. And certainly 40% error total range is probably not good enough if this is an important factor. So we need some sort of better truth, and that's what this talk will eventually get to. We need some of Fermi's clear picture. See the little icons, bad, good. Okay. Okay, so what actually do models of the ocean surface boundary layer look like? Well, this has been going on for 60 years. The first paper was in 1966 with some guys from Cambridge. There's still an amazingly wide divergence of the assumed physics. Some people want to do a turbulent kinetic energy budget. Some people want to do second order closure. Some people want to do a momentum budget. Some people put waves in, other people don't. And this talks a lot about local and non-local assumptions. They can't all be right. There can't be all these different physics that are all right. And so somebody's an elephant. Somebody's just making up a model and fitting it, and you'll see it's going to evolve. So let's look at one of the most popular ones. This is called KPP. Doesn't matter what that's. That's a 30-year-old model. I was a young guy when I had something to do with the formation of this. Very standard sort of mixing model. You've got some fluxes in a boundary layer. The fluxes, some sort of fluxes like this. You've got some diffusivity. You've got some gradient and some non-local term. And the thing you got to say is what's the diffusivity? Okay, perfectly standard model. And you specify the diffusivity by some length scale that's a function of depth, and some velocity scale that's a function of depth, and some length scale that's a function of depth, and a lot of parameters. And maybe there's adjustable parameter that you tune to make it work best. Very straightforward stuff. That thing's cubic because that's the smallest degrees of freedom that can make anything sensible. And there's some sensible scheme for making this. There's something called Money-Novikov scaling, which isn't quite right. That's used to set up some of the parameters. And then the bizarrest thing is the depth of the layer is set by a Bulk-Richardson number. Nobody knows why, which is sort of disturbing that nobody knows why. It's in lots of the climate models, but that's what it is. And there's another adjustable parameter here that you could add in here to make it different. Really nice paper by Liang, who actually was a postdoc of mine at one point, but he didn't do anything when he was a postdoc. He's gone on to be very successful, but he just didn't work out. Not all postdocs work out. Okay, and he said, okay, let's take this scheme. So what's the point here? The point here is you've got some formula, some equations, and you think that by using those equations, you're going to be better than purely empirical. That's the point of having the equations. That's the physical insight. They said, oh, we've got these two adjustable parameters, epsilon and nu, and I'm going to tune those using neural networks to a large ensemble of simulations and make them function of all the parameters I can think of. And those parameters, when you do that, vary by a factor of 7. Meaning that all the physics has now been stuck into these parameters, and this formulation has nothing to do with the physics. So this is clearly not working very well. It's not a clear dynamical picture. There we go. It's an elephant. Okay. I'm accusing everything being an elephant. Well, okay. I may get my comeuppance, but we're just going down. And the point is, maybe if you had a different structure to the model, things would be better, and you're actually using your physical insight to write that. And that's the pursuit. I will get close to that. Mostly it's the path, not necessarily where you get to, and that's what you're going to see about it. Okay. So how do we get better truth? Well, a long time ago, I was a young guy. I was flying this airplane over the Northeast Pacific in an experiment called the Ocean Storms Experiment that I helped organize. Ocean surface under those conditions looks sort of like this. There's lots of waves. This is what the ocean surface looks like in 25 meter a second winds. There's lots of waves. They're breaking, lots of bubbles. It's a complicated situation. I was looking at all of this and saying, whatever work I had to do was done. This is really a complicated system. And we don't have any measurements that are even close to figuring out what's going on here. What could we do that was better in terms of measurements? Because I was a measurement guy and I was at a measurement place. But this is good. This is good. This is how new ideas come by. You do that. And then I talked to all my friends. And I was working with a guy named David Farmer, who was a pretty famous fluid dynamicist in British Columbia. And he had talked to some Russians, and they had built instruments that would be Lagrangian, made out of vodka and gasoline, because that's what they had. Okay. And he said, why don't you try that? Well, this is how good ideas come. You've got some old guy who's got more ideas than he knows what to do with it, and some young guy that's trying to figure it out. Then things move on. Good. Talk to your friends. Okay. So the idea was to make Lagrangian measurements of turbulence in this boundary layer. This turned out to be a good idea. If you have a really good idea, it's worth a whole career because your life isn't really that long. I should know. And so, yeah, that's good. 2 or 3 ideas is better than one, but one is better, a whole lot better than none. Okay, here's the basic idea is that when you make Lagrangian measurements of turbulence, you get a lot of insight in a really simple way. So this is an example, a few years into this project. I won't talk right now about how we made the measurements. That's the next slide. But just imagine that you've got some measurements. So this is depth of the ocean, the upper 100 meters. This is time of day ensembled over a week, say. And this time of day, it's sunny, daytime. This time of day, it's not sunny. And this time of day, this is called night. And during the day, it's sunny, and at night, it's dark. So there's no solar radiation at night. And these are a bunch of trajectories, of Lagrangian trajectories. And you can see they give a very nice intuitive idea of what's happening. A parcel at the water goes down, it comes up. How fast is the mixing? What about the time it takes to go from the bottom to back up again? The mixing gets deeper over time because there is nighttime convection, and this is stratified water, and it chews away at the stratified water. So you get a really clear idea what happens just from this picture. That's good progress. Very turbulent concepts translate easily. I'll talk about that in the next few slides. And then there's a couple of really important things. This is the equation for a conserved quantity, like temperature or what else? Concentration of salt or other things. The Lagrangian equation for a conserved quantity, that's all there is. The Lagrangian rate of change of something is equal to the molecular diffusivity. That's all there is. It's not complicated. There's no nonlinearity. The nonlinearity shows up someplace else, but there's no nonlinearity if you're making these measurements. And so you can measure the molecular diffusion rate just from the rate of change of this quantity. That's a very direct measure of mixing. That is mixing. That is undeniably mixing. Other things might be mixing, but that one is. Okay. There are also some very unique advantages of these techniques just for the ocean surface boundary layer. There's a huge problem, and that is the turbulence velocities are a centimeter a second, and the surface waves are a meter a second, and the currents are a tenth of a meter a second, and so you've got a signal to noise of 0.01. You need a signal to noise of maybe 100, so that means your instrument would have to be linear to 1 part in 10 to the 4th, and you can't do that. So this is a big problem. It turns out that if you measure Lagrangian trajectories from making pressure be your depth, pressure automatically filters out the surface waves. Surface waves have no pressure fluctuations along trajectory to second order in the amplitude of the surface waves. So that's really good. And if there's some sort of enormous current, if you're Lagrangian, you're just following along with the water, so you don't care if there's a big current. So this is two really big advantages, and has really made this effective. Okay, here's how we do it. We've gone through several iterations, but this is now quite mature. This is an instrument called a Lagrangian float. That's what it looks like. It's the size of a person. I don't like things bigger than me, because if they fall on me, they'll hurt me. So I like things that are smaller. The goal is to follow water parcels in 3 dimensions in the ocean while measuring the position and the water properties. So what it looks like, we can measure the water properties from instruments on the top and the bottom. I won't talk about that in detail. The way you do that is you make it neutrally buoyant, really, really neutrally buoyant. And you have a high drag. And what it has is a little piston, or a pretty big piston, almost a liter worth of piston that pushes in and out of the bottom, that's computer controlled based on what the density of the water is, which we measure. And we have to know the density of this instrument as it's compressed and as it warms and cools. And you do all, and this is not easy to do, but we can match the density of this instrument, that's a 50-liter instrument, to that of the water to a few grams. That's almost a 1 part in 10 to the 5th operations. It's hard. And we're doing this for a long time now, and we've used it in all sorts of places all over the world, not just for this problem, but for other problems, and importantly, under a wide range of boundary conditions. This is a regime diagram from a student of ours that graduated recently, where this is convection over here, surface cooling. This is shear driven. This is wave driven, and with unstable buoyancy fluxes or with stable buoyancy fluxes. So we have a big ensemble of data that we're now mining of all sorts of different conditions. And this is where the ocean lives. Sometimes in convection, sometimes in wave driven, very rarely in shear driven. This is a big change in the last couple decades, that your classic models of turbulence are driven by shear. That's not the dominant form by which turbulence is driven in the upper ocean. It's got to do with wave driven, which is a whole different lecture, but just take it as that. Okay, so backwards, that way. What interesting things can we measure, and how do we know the measurements are right? If you're measuring a new quantity, everyone will say, well, I don't think it should look like that. How do you know it's right? Because it's a new thing, so nobody else is measuring it. So how can you prove to other people that it's right? A fundamental quantity in turbulence theory is the idea of inertial subranges and dissipation rate. The classic paper is by Grant in 1962, which was taken in the picture you see in the background up in British Columbia, these tidal channels, really, really high Reynolds number. And if you measure the horizontal wave number of velocity, you get a minus 5/3 spectrum, and the dissipation's down here, and this is an inertial subrange. And from that level of the spectrum, you can get the dissipation rate. If you know what I'm talking about, you know what I'm talking about. Otherwise, this is a mystery. Okay, be that as it may. There's a Lagrangian, there's an inertial subrange for acceleration also. This is from some laboratory and numerical simulations. Turns out that the right way to say it is that acceleration is white. Okay. We can do that. Oh, okay. This is what it looks like up in British Columbia there. Here's Canada, here's US, it's right up there on the inside of Vancouver Island. This is a giant whirlpool. Those are really big logs. If you fall in the water here and you're wearing a life preserver, you'll go blub, blub, blub down here along with the giant log. So don't do that. But there's plenty of high Reynolds number turbulence there for sure. Okay, if you apply this to a lot of Lagrangian float data, you see a white spectrum and an instrument response. And therefore we can get dissipation rates and all sorts of stuff like that. So that's just a check. It's been useful. Okay. Subtler thing to measure would be vertical kinetic energy. How much something is going up and down. You can measure that from the rate of change of pressure, like I said, and you can square it and you get a profile and you sort of expect it to scale with the wind stress, the momentum going into the ocean. And in a shear-driven boundary layer, it's that green curve. The green curve, which is real data taken from a lake. And these are curves taken from the open ocean. It's bigger than that. That's the difference between wave forcing and just stress forcing. And that took a decade to get all that data and do it all right, but it worked. How do we know it's right? Well, one thing is the float should be mixed up like everything else. There's a mixed layer. So since temperature is mixed, the float should be mixed too. That means the PDF of float depth should be uniform. You can check that. I'll show an example. Subtler thing is, let's look at the expression for vertical acceleration. dw dt is the Eulerian derivative plus w times dw dz plus horizontal terms. If it's horizontally homogeneous and you average, those terms go away. You get that expression. You integrate it once. You end up with w squared is equal to the integral of the acceleration over depth. That's just true. That's only works if you're measuring Lagrangian. And now I have two measurements of W from completely different things, W, and so I can check that they're the same. And sometimes that really works out nicely. This is an example of everything working out nicely. This was in the Bay of Bengal in the southwest monsoon about a decade ago. The wind is blowing, wind is pretty steady, a good strong wind. There's a steady light rain, and it's cooling. Okay, and this is what the float does. It goes up and down. Don't worry about the color right now. So, and down to about 30 meters, and it's always going to 30 meters over almost a whole day. Okay, the gray is the PDF of depth, pretty uniform. Not as good as you can get, down to about 20 meters, and then these, down below 20 meters, sometimes they're there and sometimes they're not. Okay, that's what it should be. The W squared computed from computing W and squaring it is the black curve. And from computing the acceleration integrated over depth, it's the red curve. And they pretty much lie on each other. Okay, so that's a solid consistency test. That's about as good as we can do. Not perfect, but and you, of course, can test this stuff in simulations too. But I'm not talking about simulations. Okay. Another thing you can do, interesting statistics. You can look at skewness, the cube of the velocity. And it's always negative. What that means is that the downs are faster than the ups. And why are the downs faster than the up? Because the layer is being forced at the surface. You're energizing at the surface, then it goes down. Well, if it goes down, it has to come up. So it comes up weakly, goes down strong. And that's true regardless of whether you're forcing it by, oh, look at that. What do you know? That's true whether or not you're forcing it with convection or with waves. And the values you get are sort of, for pure shear-driven layer is sort of the green curve, just a little bit negative. That's what it should be theoretically from LAS simulations. And if you're in the open ocean, you get more like a half or something like that. And that's what LAS simulations show. So it's all pretty consistent. And it says that the flow is not vertically symmetric. Down is faster than up. That's a lack of vertical symmetry. That'll show up. Okay. Now, you can not just do vertical velocity. You can do another interesting. You can do fluxes. Everybody loves fluxes. And what that says is, here's the heat equation, say, the Lagrangian change in temperature is equal to the Eulerian change in temperature, how much the layer is heating up or cooling down. plus the divergence of a covariance flux and horizontal terms and mixing. Okay. What happens in a Lagrangian view of, say, convection? That's this diagram here. So this is temperature, don't worry about the word potential, on this axis, depth on this axis, and this is a phase diagram. So suppose I'm a piece of water and I'm sitting near the surface of the ocean, and the water is cooling. Well, it'll get colder. What else? What could it do besides getting colder? It's being cold. Then it goes down, and in the interior of the ocean, there's no heating or cooling. So the parcel can't change temperature on average. So the simplest thing is it doesn't change temperature at all, and it goes down, and it comes up again, and gets back to the surface, and it cools off again. Okay, that's pretty simple. Seems a lot simpler than W prime, T prime and things. Nice. Let's look at now W. It's not W theta, it's W prime times theta prime. W is a mean of 0, so it's the prime of this. So now let's look at the deviation of the temperature from the average. Well, I'm at the surface, like over here. I cool off. I start to go down. I am now the coldest parcel around because I just got cooled off. Everybody else hasn't gotten cooled off. So I'm the coldest parcel. As I go down, my temperature stays constant, but everybody else cools off. So my perturbation temperature goes up. Keeps on going up, and I repeat. It's easy to show that the area of this curve is the flux. Okay? And you can actually compute the flux by the area integrated that way or the area integrated that way, but I'm going to do that mathematically. Do the same trick. Assume horizontal homogeneity, so I throw out that. The rate of change of temperature averaged over the whole layer is equal to the divergence of the flux, the area of that, plus this other term, which is the heating and cooling from molecular diffusion. I can write that as a change is equal to a depth derivative of that guy and the integral of that guy. And those are 3 terms, and I can look at them over here. This term is that curve there. You heat up in the surface, and you don't heat up there. So when you extrapolate this to the surface, you get the cooling rate. And the other one is the normal one, the buoyancy flux, and you extrapolate it to the surface, and you get the cooling rate. So I got 2 measurements of heat flux, and that means I can check it. So here's an example of where that works well. This is the same example I showed you before. Here's the curve. In red is the standard heat flux. It's straight line. It's just about 0 at the bottom, meaning not much interesting is happening at the bottom. At the surface, it extrapolates to some number about like that. I look at the rate of change of the rate of change of this guy. Okay, that's this curve. It is constant in the interior because there's no heating or cooling, and it's cooling in the surface. And those 2 numbers come out the same. So I can measure surface heat flux in 2 different ways. Works out pretty well. Okay, so far I've been using Lagrangian measurements to compute Eulerian statistics, and I was stuck on that for a long time. And then my postdoc, this is another reason that young people should talk to old people and the other way around. My postdoc said, "Hey, this stuff with the fluxes is really cool. Why have you stopped doing that?" I said, I don't know, I just forgot. I got distracted. So let's talk about Lagrangian statistics. Now, in turbulence theory, there's this concept of a length scale. Eddies are so big, but this is really abstract. What is an eddy? Why is it so big? What does that mean? Usually it's some coefficient in a model. In a Lagrangian sense, it's a very concrete thing. Black line is an actual trajectory of a particle in a mixed layer in the North Pacific sometime. It's at the surface, it goes down. How big is the eddy? Well, it went down here and it turned around there, so the distance is that distance. And similarly on an upcast, it goes from there to there, and I can take them and I can classify them by where they started and where they ended, and I can start looking at real statistics of what the length scale is. And it's a real measurable quantity. Here's what the statistics look like. Okay. This is the statistics of the starting depth of downward going trajectories. And this is the statistics of the starting depth of upward going trajectories or the ending depth of a downward going trajectory, because a down always is followed by an up. What you see is a whole lot of data. About 50% is up here in the top 20%. In other words, half the downward segments start in the upper 20% of the mixed layer. This is normalized by mixed layer depth. The downs are uniform distribution. That's a straight line, meaning the ups start at random depth, the downs start at the surface, is the simple way of thinking about it. They start at the surface. It's sort of easy to understand why. Well, it's forced at the surface, so that's where they start. Okay. That's interesting. They're different colored curves. This is from all sorts of places. All over the world, the curves are all the same. So this is really good. No matter how it's forced, these scales are pretty much the same. That's cool. Okay, you can derive that result really lovely using very classical turbulence theory. I'm going to simulate trajectories with a Gaussian Langevin equation, meaning I say I'm going to have some trajectories, and whatever the trajectories look like, their RMSW has to equal whatever it is in the observation. So that's easy enough to do. And I assume the Lagrangian acceleration is white. That's what you should have for a turbulent flow. And that means that you integrate the velocity. You just make random accelerations. You integrate them, you get a velocity. You double integrate them, you get a displacement. The acceleration spectrum is white. The vertical velocity spectrum is -2. The displacement is -4, which means almost all the energy is in the largest scales. That's why LAS models work. So it's not very surprising then that you're trying to make a spectrum which is really, really dominated by big scales. It'll only fit if it starts at the beginning. If it starts at the top and ends to the bottom, then most of the eddies are big. And that's a simulation by these assumptions. Is this heavy curve, and that's one of the other curves. And parcels have to bounce off the surface. We've got it going up. If it's the surface, it bounces. If I made the bouncing region just a little bit thicker than the surface, I could almost exactly duplicate the data. That's on the downs. On the ups, it's a symmetrical model. So the ups have to be the same as the downs. They're not. So something different is happening in the ups than in the downs. Again, it's profoundly asymmetric up-down. Okay. Final thing you need to make a transport model out of this all is, so far I've just talked about where the parcels go. And maybe that got cooled off at the surface. Well, if you cool off a parcel at the surface and it goes down, does it keep that temperature or does it get a different temperature? Well, here's a simple version of that. So I've got a bunch of trajectories and a wind force boundary. Every time I'm going to start counting them, and I'm going to define all the tops, the near surface tops, all those points there, and I'm going to look at data on either side of a surfacing like that. Okay, that's a sensible thing to do. So here's where it got to the surface, and here's the up, and here's the down, and this is in a warming case, and here's an up, and here's a down. That's in a cooling case. The color is the temperature. Well, it's pretty clear what's happening. When it's going up, it's cold, and then it warms up, and then it goes down. And even in the cooling case, you see the stronger. These are all red, and these are all blue. All the change happened here. So the first order, basically all the change happens here. Not much happens here. Not much happens here. You can plot for the cooling case what the rate of change of temperature is as a function of depth, and it's pretty much constant and zero, meaning not much is happening. In this case, because during the daytime, the heating occurs by solar radiation, which is absorbed over a layer. There's a warming layer here. That's why they're curved. But ignoring those, take the nighttime ones, it's pretty flat. So that leads to at least a conceptual transport model. Said goes to the pieces. Water in the surface layer converges. It goes down and stops with a uniform distribution at all depths. In other words, there's a big plume here, and then it peels off on the way down, and maybe a little bit of it goes all the way to the bottom and hits the bottom. So this has got a lot to do with entrainment theory, which I'm barely going to touch on because I don't understand it yet. And then it goes up, slower, which is why the arrows are smaller. And add the additional thing that during these plumes, the temperature that a piece of water has is just what it got at the surface. This is a non-local transport model for sure. It's vertically asymmetric, and therefore it's not well characterized by a diffusivity. A diffusivity says that I've got little eddies and they all add up. This is the exact opposite. Most of the eddies are so big they won't even fit in the layer. So if you remember, I was talking about KPP, but it applies to almost all other parameterization models and maybe some models that you're using for other purposes. It's physically inconsistent with standard turbulence theory, and it's physically inconsistent with the observations. And this is not news. You've heard people say this before if you've been around for a while. Tennekes and Lumley, the famous book on turbulence, chapter 1, the entire chapter 1 of Tennekes and Lumley is full of statements like this. Eddy diffusivity is a dangerous approach. However, it often makes the mathematics a good deal simpler. It cannot be stressed too strongly that what? Eddy diffusivity is an artifice which may or may not represent the effects of turbulence faithfully. And if you didn't believe that, you could say success in turbulence model depends strongly on the inspiration involved in making the crucial assumptions, which is exactly what Fermi said. You have to have a clear physical insight. And the claim here is that a model like this is closer to a clear physical picture than a diffusive model. Okay. You can leave now, but just same thing. Okay, let's talk about, you've got a mixed layer in the upper ocean. How does it mix? Well, I've got two possible models. I could have a diffusion model. This is depth, this is time. I'm starting out with a white, and the color is temperature. Starting out with a white temperature, I'm going to impose a diffusivity, one parameter, and have no flux at the bottom and flux at the top. And this curvature is because I couldn't figure out what sensibly to do with the flux to make it not curve at the bottom. Okay, just solve that equation. What do you see? Well, you know what? You heat it at the top and it got warmer. Good. And it gets warmer deeper later because it takes some time for parcels, for the water to heat up at depth. An alternative model, it's a plume model. I go to the surface, I heat up at the surface, I go down. I specify one parameter, just like I did here. Instead of diffusivity, I specify one parameter, the vertical velocity. That's all I got to specify. And, well, first it heats up, and it takes longer to heat up at the bottom than the top because it takes a while for parcels to get down there. One parameter model. In the limit of either really big W or really big diffusion, that time lag goes to nothing, and I get a slab model. It's basically constant temperature with depth. If it's constant temperature with depth and it heats, then the buoyancy flux, the heat flux must necessarily be a straight line. So all models that have, almost all models of this system will have a heat flux profile that's a straight line, and they'll all have it because you wouldn't publish a model that didn't have a straight line. So it's meaningless. The buoyancy flux profile is meaningless. Just got to be a straight line. On the other hand, what's the rate? What's the Lagrangian heating rate? It's not. You don't want to see that. Yeah, almost. What's the Lagrangian heating rate? Well, in this case, in the diffusive case, it's constant depth almost. In other words, how does a parcel of water in this model get warmer? If I'm at this depth, how do I say the water gets warmer? I say it gets warmer by mixing with the parcel above it, which is even warmer, and the top parcel is warmed by the heat flux. Perfectly straightforward diffusive model. Same thing, it can be a fluid or it can be a block of steel. Same thing happens. How, in this case, does a parcel of water warm? An interior parcel gets warmer by going to the surface, warming up, and going back down again. Very different physics, and it's nicely expressed by the Lagrangian rate of heating, which is a intrinsically Lagrangian quantity. Okay, one more slide after this. Then we get time for questions. Time's just about right. I hope I've convinced you that Lagrangian measures of turbulence can make some unique insights, and in a numerical model, it's not really very difficult to do, but it doesn't seem to be a very standard thing to do. So I'm on my soapbox. For the upper ocean, they suggest a new way of thinking about the way the transport works. Parcels start at the surface, they go to a random depth, they return, they go down faster than up. Subsurface parcels carry the properties of the surface layer. These observations are inconsistent with diffusive closures, and all the important mixing happens in the surface layer. In other words, one of the things which I've always wondered about is there have been quite a few measurements of turbulence. These are unique in their own way, but it's quite routine now to make what are called microstructure measurements in the ocean. And that's a measure of the dissipation rate of kinetic energy, turbulent kinetic energy, and often of temperature too. Been quite a few measurements, and that has had essentially no impact on the models. Well, why not? Well, the reason is that they can't measure right next to the surface. There's a whole bunch of people that work on breaking surface waves, but if you're not, but they use different methods. If you're working in the interior, what's the balance of turbulent kinetic energy in the middle of the boundary layer? It's that a parcel is at the surface, the mixing is really intense. The mixing in the middle of the ocean, in the middle of the ocean boundary layer might be 10 to the minus 5 watts per kilogram. In a breaking wave at the surface, the dissipation rate is 1. 1 is enough to tear, you know how the surface of the ocean is breaking waves and it's got all that foam? In order to break apart the surface tension and make it energetic, you need a dissipation rate of about 1 watt per kilogram. Middle of the ocean, it's 10 to the 5th. That's 100,000 times less. So maybe it's not surprising that the little bit of mixing that happens in the interior is irrelevant, because that's the extreme example. But also what the balance is that a parcel of water has lots of turbulence in the surface. It goes down. As it's going down, that turbulence is decaying, and the balance is the export of turbulence from the boundary layer to dissipation. That really doesn't tell you very much. It's nothing like a production equals dissipation model. That's probably why those haven't much impact. It's not irrelevant. Okay, I'm hoping to add horizontal velocity and shear information, and we should do comparisons with LES. Okay, this is fun. I'm basically claiming that I have a clear picture, and all the rest of you are wrong. Okay, well, time will tell whether this is really true or not. But either way, it's fun. But the big issue with this is that the most important property of the boundary layer is how thick it is. And it varies a lot. If we go way, way back to this thing I did a long time ago, this. The most interesting thing that happened is the layer during the daytime is maybe 10 meters thick, and during the nighttime it's 70 meters thick. That's the most interesting thing. That's what the climate models care about. They don't care about all this stuff about how it mixes. They care about how deep the layer is. And nothing in what I've said so far has reflected on what that physics is, except perhaps the idea that it's probably got something to do with export, and the fact that plumes right into the bottom is probably important. But that's just incidental comments. So the entrainment is really the hard part of the problem. Well, okay, that's good. Okay. I could say I don't understand the physics of entrainment at all. This is a hard problem. It's a really classical, difficult problem in stratified turbulence. Stratified turbulence can have waves and it can have turbulence. So I like to tease theoreticians with this following statement. Parameterizations of stratified turbulence that do not include the internal wave dispersion relationship are wrong. There are waves in stratified fluid. If your parameterization of turbulence doesn't have waves, it's missing probably an important thing. Okay, and you see lots of evidence of waves in the upper ocean, big peaks near end. And here are 2 quick examples of how this is important. Okay, let's see, can I make this go? Can I make it go? Let's try it. Go? No. Try 2, and then we'll give up. Can't even find the mouse. There. Click, click, click. I give up. Okay. What you would see in this picture, this is an LES simulation of the bottom of the mixed. This is the surface at the bottom of the mixed layer. if you saw the movie, it would be running along here, would look like a sea. It would look like the surface of the ocean with all these red patches being breaking waves. It just looks like a whole sea of waves that are running in that direction. So that sort of shows there's waves. I'm working here with Connor Bryans and his student, hi, on this problem, which I think is a very important problem. We have a boundary layer, it's got turbulence in it, and the turbulence bangs on the bottom of the boundary layer and it radiates waves. That's a big sink of energy. And how strong it's doing that and when it does it and when it isn't is a big issue in the energy balance of how the entrainment works. And nothing like this is in any of the entrainment models. So there's a lot more to learn about that. And I think that's the most important problem right now. And maybe we'll make some progress on it. So anyway, thank you. That was fun, I hope. Now, I really want some questions. After all, everything I said, I already knew. I knew that already. But what I hear from you is stuff I don't know or things I haven't thought of. So please ask questions.
Questions?
Oh, come on.
I'm
Good.
completely not related to this field.
That's
I'm
better.
an electrical engineer.
Yeah.
So it looks like making measurements seems to be a very difficult problem itself.
Yeah, it is very difficult.
So have there been attempts to actually emulate the ocean in terms of artificially, using these things to see if your measurements sort of...
Oh, yeah. So it was obviously it's almost impossible in a talk like this to avoid using your field's jargon. Just impossible. The biggest thing that's happened in this field in the last 20 or 30 years has been the evolution of large eddy simulations, and they have become the standard for building models. I have some issues with that, but it's clearly led to a whole lot of progress. And so, I mean, the example which I showed of how good are the models essentially. Come on, this diagram, that is parameterizations versus LES, because there wasn't anything else better for truth. And I've made this very data-centric sort of intentionally to emphasize the data, but a lot of this stuff has been checked out and can be checked out against simulations. I guess the main reason I've been using data is because my collaborator for the LES stuff, Ramsey Harkart, has been doing other stuff. And he says he's too busy to talk to me about it. Anyway, so yeah, I mean, clearly that's like in all fields. It's been a real enormous effect.
For this convective fluid,
Yeah.
get stopped at intermediate position.
Yeah.
So do we understand that well? Is it because of
Well, the simple story. Whoops, wrong way. The simple story is. The simple story is that one. If I do a statistical model that just says acceleration is white, then some of the plumes go all the way down and some of them turn around. Now, so that's the simplest answer. In a random walk, some guys go further and some guys don't. On the other hand, it really is governed by plumes, and presumably the one that, if I go forward a little bit more. Okay, so here's a sort of a model. If you look really carefully, you might have noticed that the surface is a little bit higher there than there. That's intentional. So there's high pressure at the surface, which is driving this down. And if you happen to be lucky, some guys will be bigger and some guys will be smaller. Just by random, it's either random, or it can also be that, for instance, there's a gust of wind that makes it extra strong, or the gust of wind coinciding with a wave group that happens to be large, and then you get a particularly energetic guy, and that's much more likely to go all the way down and run into the bottom, and then a weak one. And it's a turbulent flow, so there's also there's an eddy, and some guys are going around the middle of the eddy, and some guys are going around the outside. So if you do a 2D, in 2D turbulence, the eddies get really big. And if you do a 2D model, then then you get really strong plumes. And basically you get a big cell that goes around like that. And that's not realistic. It gives you some insight, but it's not a realistic model. Because in 3D, it's much more chaotic.
Follow up, so pixel holds even in language of
Yes, that was the very surprising thing which got me sort of going on this. That is, in this diagram here, the green one is in a lake, in a lake near us. The red one in a layer that's maybe 20 meters thick. The red one is in a 500 meter thick layer in the Labrador Sea in the middle of winter. That one's convective. It's probably convective with a little bit of rotational effects. It does not seem to make much difference where you are. This geometrical constraint of having a system that wants to have really big eddies, but is bounded by walls, essentially, seems to make this geometry of it independent of the details of the forcing. What changes is how fast you go down, and probably a bunch of other statistics. But that's the whole key. It's okay. There's something here which is universal that we can look on. Very much in the same way that in a diffusive model, you would say, here's the length scale as a function of depth. This is a different way to say it. Better, I think.
Other questions?
You could ask questions. You could ask a question of how the floats work. I could talk for that for the rest for as long as you'd like.
So when the floats experience a change in the currents,
Yeah.
is there a relaxation time for?
Oh, yeah. Okay. So that's a wonderful question. And in another version of this talk, I actually had a quiz about that, but that people didn't like quizzes. They required them to wake up, so I dropped that part of the talk. Think of a piece of water in the ocean, and the piece of water is F equals ma. If there's no force on it, it just keeps moving at the same speed. And if there's a float there and it's moving in the middle of that water and it's moving, it'll keep on going. If it has to speed up, that means there has to be a force on it. The force on it is due to the pressure gradient on either side of it. And that pressure gradient will act on the water in the same way that it acts on the float. F equals ma. If the mass of the float is different than the mass of the water, it will accelerate differently. But if you make the masses the same, they will accelerate the same. Now, of course, if the float is a different mass of the water, it'll also be heavy and it will sink like a rock, exactly like a rock. Which is a bigger effect. So the trick is there is no lag because the forces that make the water go are the same as the forces that make the float go. But I have a blob of water. Half of the water can go that way and half of the water can go that way. And there's only one float and it has to do something in between. And that's the backwards. That's this response function here. That the float at high frequencies, the float doesn't follow the water because because it's the same size as the eddies. And so that's but this curve is almost always the same, which is just saying that there's a universal property. So we can apply that in many circumstances.
The communication from the float is through what?
Through Iridium,
Through radio.
Iridium satellite.
Oh,
So it's done by satellite comms. The key enabling technologies for this and a great many other oceanographic instruments are the same technologies that make your cell phone work: satellite communication, microelectronics, lithium batteries. Those are essential. What we could do.
so you have to go replace the battery every now and then.
Yeah. So we have intentionally. You could make floats. You would say, well, why don't you make a float this big? There would be less bias. The problem is because the volume goes up as the cube. As the thing gets bigger, you could hold a lot more batteries. We just decided that what we wanted was lots of data, and therefore make it bigger, carry lots of instruments, and that would be a better payoff scientifically than making small ones. We can go for months depending on the payload, and we've made there are lots of different sensors you can carry, and that's a whole story in itself. All of which are also enabled by the same things that enable your phone to work.
Communication happens like once 24 hours.
Whenever we surface, we can communicate, and that's totally under our control.
But won't that be a waste of battery?
Well, you also want to know where it is. So the trade-off is if you surface, you now get a GPS fix. Otherwise, you can do acoustic tracking, but it's very difficult, and you pay so much in the inconvenience cost of doing acoustic tracking that you're better off just working in the vertical and getting data in a whole lot more places, except for very specialized things. We've done the acoustic tracking. It works. It's difficult and mostly complicated. That's why submarines can hide well, because it's in the water. It's really hard to figure out where they are, basically. Yeah.
So these up and down motions of the fluid parcels.
Yeah.
You show one of those slides.
Yeah,
that
yeah.
Shows
With a
24-hour period.
Yeah, we'll do the classic one. That one.
Yeah.
That's the best one. Yeah.
So what is the time period that is present in the up and down motions?
An hour or so. I mean, depends. Obviously it takes longer to go this far than it takes to go that far. But here we got 1, 2, 3, 4, 6, 7, 8, 10 in 24 hours.
And
So
what sets that?
It scales with the vertical velocity divided by the depth of the layer. It's just how long it takes to go down, how fast it's going. The RMS vertical velocity is is what's called U star, the velocity equivalent of the wind stress.
Yeah.
So that scales very closely with that. So we know that number pretty well.
Any other questions?
Yeah.
Yes.
Hey. Oh, okay. So he asked. So here's a 70 meter mix. How big is the float? So this is 10 meters. So the float is about that big. So the ratio of the size of the float to the depth of the layer in this case is a fairly small parameter, and we know how to correct for the finite size in many parameters. So we can take care of that issue. If you're in a layer that's only this big, then a float that's that big is a real problem when we try to avoid that situation. Now, you've still got a truck. You can still instrument the float and have it be there, but it's no longer a Lagrangian measurement. It's just a truck carrying an interesting set of instruments, which is a useful thing in itself. Okay.
Any other questions? Okay. If there are no other questions, let's thank Eric once more.
Thank you.